So in this video, we're going to discuss electromagnetic induction. Here, now we're into electromagnetic induction. Electromagnetic induction. What we have seen in the previous chapter is we saw a moving charge, moving electric charge, right? This is also called a current. So again, this has to be moving, not just the electric charge, but it's moving, and this generates a magnetic field. Right? dq dt generates magnetic field. And also we saw a magnetic force. Exerts on, what is it? Moving charge. So we saw relationship connecting to moving electrons generates magnetic field, magnetic force applied on the moving electric charge. So we see the crossover electromagnetism, right? Here, I'm going to show you a video. So this is this. I have a wire, copper wire. This orange thing is the copper wire wrapped around. I just wanted to make a closed loop. And I made 700 turns and connected two ends with LED light. That's it. Nothing else. It's just making a nice closed loop. And of course, no battery. That's it. Hello. So what do we have here? What's this white stuff? What's this white stuff?
Toilet paper roll.
Toilet paper roll. And I put copper wires around it. How many turns do you remember Mommy turned it diligently?
700.
700 turns.
700.
700. So yeah, and you see it's just around the toilet paper roll. There's nothing else. And then two ends are connected with LED. That's it. There's no power source. It's just a loops of wires and light. So what else I have here is the neodyme magnet. So now I have a neodyme magnet. Let's see what happens if my husband, I guess, or I were to drop that neodyme magnet through the loop, inside the loop. What happens? All right, one more time.
Okay.
All right.
1, 2, 3, go.
Yeah, it lit.
You got it?
Okay. Do again, please. I'm a little more focused.
All right, why don't you see the light?
Yeah.
Here.
Here. Okay.
Good?
Yeah.
More?
Yeah. Aha. Did you see it? It lit. It lit, dropping a magnet through inside a coil, lit the light, what happened? What happened? It induced current, electric current. So here, what you're seeing is that changing magnetic field. Changing magnetic field induces electric current. Changing magnetic field induces voltage. And again, this, of course, the circuit, the loop has to be closed. Otherwise, you don't have a current running, right? So that's why I make sure to have it all closed up. And then magnetic field, that's neodymium magnet pass through, right? Approaching it, increasing magnetic field, leaving it, decreasing magnetic field. So changing, if I'm just putting a magnet and stationary, it won't induce. It has to be the change in magnetic field passing through induces current and therefore induces voltage. So here, instead of just dropping it, we're going to go up and down, up and down. So constantly change magnetic field. Okay, now you see in and out, in and out. Change in magnetic field induces current in a wire. Induce current, induce voltage. So it's not connected to the battery. It's just a change in magnetic field. And the one we have, the magnet again, is the neodymium magnet. Right? All right, say bye.
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 Bye. All right, so that's what you saw. Changing magnetic field induces electric current, electric voltage. That's called electromagnetic induction. And you see, so of course, the bigger change in magnetic field induces bigger current, bigger voltage. And number of loops that you make matters, changes the induction of a current or induction of a voltage. Let me share the notes. So here's the notes. And so what we have just seen is changing the magnetic field. Means induce electric current. So it has to be in a closed loop. Otherwise, the current won't flow. Also, the number of turns matter. How much the big change in magnetic field matters. So we call this Faraday's law. Faraday put this idea. That says the induced. It's actually better to use the voltage because current depends on the resistance. So it depends on the material. But induced voltage, that depends on how much change in the magnetic field and also the number of turns in the area. So the induced voltage in a coil is proportional to the product of its number of loops. The cross-sectional area and the rate at, sorry, which the magnetic field changes within those So Faraday's law put this idea, you will see voltage induced in a closed loop when you have the change in magnetic field. Then the induced voltage depends on the number of loops on the coil and also depends on cross-sectional area of each loop, right? The size matter, area, and the number of turns. And also how fast, how much magnetic field passing by changing. So that's what the Faraday's law say. You see this application everywhere. You see this everywhere. But before that, let me share this video. So this is these two are the metal, right? The key thing is that it has a hole and it's a closed ring, and you can drop magnet ball. Okay, so again. Uh-oh. So what we have seen is this, this is the magnetic ball that's passing through the loop or the big ring of metal. So when the magnetic ball approaches to the cylinder with a hole, the cylinder, metallic cylinder feels the change in magnetic field, so it induces voltage current. But this current is induced to oppose the change in magnetic field. Nature doesn't like the change. It doesn't like the change. So this, the loop, they feel that, oh my goodness, the magnetic field is approaching, its intensity is increasing. Then you use this right-hand rule. So let's say the magnetic field is coming, right? The ball has the north on this end, and then that's approaching. And this is the tube, right? The tube here coming towards it. They don't like the change. Oh my goodness, the magnetic field is increasing. So they induce the current in a way to oppose the change in magnetic field. So if it's increasing magnetic field, the current will run in this direction to generate the magnetic field to oppose the change. Right? This way, so oppose the change. Coming this way, oppose the change. So that's why it slows down the ball, because it's inducing the current, also induces the magnetic field to oppose the change, so to slow down the ball. The ball is a magnet ball, so it feels the this magnetic field induced by this current that induces its own changing magnetic field. All right, so nature doesn't like to change. So that's one of the example. Um, Traffic light. Have you noticed when you're driving and then you stop at the traffic signal? Have you noticed on the ground that you have a big loop embedded? That detects the car that's approached. So then traffic signal, hopefully it changes from red to green for you, right? But the triggering system uses this induction to detect it. So the key thing is that loop in the ground. So this is the, maybe this one. Here you see there's the big loop. You might have seen it. You can even, I see in 10 freeway too. That's in there. To sometimes it's just to count how many cars are passing and things. So what does this do? So this is a closed loop. You could be producing a magnetic field here. So it could be coming out. What's car made of? Car is made of metal. What does metal have? Free electrons. Moving free electrons is electric current. When you have an electric current coming, the electric current induces magnetic field. So you have a magnetic field approaching to the loop that has its own magnetic field. Then it disturbs changing magnetic field, induces current in the ground that sends off the signal to the traffic light. So that's why, like when you're riding a motorcycle, you have to aim it to at the center because you want to make sure to have the changing magnetic field to be the largest. And the motorcycle just don't have enough free electrons compared to the car. You may not have as many changing magnetic field. So you want to do fast and stop quickly. It's probably better way, but I don't suggest that's a good thing. So something like that. In bicycle, you're not going fast enough, or you don't have enough free electrons. So it's going to be hard for you to trigger that traffic light using this technology. Here, credit card. So these days you can just swipe, either swipe the credit card or you can even insert the credit card. Do you think the credit card has a battery in it? It's so thin. There's no battery inside the credit card. But if we have a chip, it knows how much you're spending, right? How much you have money in your account, right? So there's a computer chip in a credit card, but there's no battery. How does it read? They use similar technology. So here is the image of the X-ray of see X-ray of credit card. There is a wire here, computer chip here that has the big loop here. Swipe it off, changing magnetic field, induce voltage. So that's how they can communicate. And this type of communication is called near field communication. And I wonder if I have it here. No. So similar thing happens with this. This is the fob key. In order to enter our campus, the classroom, the physics classroom on campus, I swipe it. Can you see? there's no place to put the battery, right? It's just a plastic all enclosed in a plastic. So I can replace the battery if there is a battery. So there is no battery inside here, but I swipe it, means that there's a loop here. There's a loop on the keypad. You swipe it, changes, disturbs the magnetic field, induces current, and that's how they can communicate with each other. There's many things. Metal detection at the airport. So you remember to pass through those metal detection, right? You pass through this big surrounded cylinder looking thing, the gate that's enclosed. Make sure you watch it. It's not just only on the top. There's a ground part and you pass through there. What if you have a metal? You have metal has free electron. Free electrons moving is called electric current. Electric current generates magnetic field. Approaching magnetic field is the change in magnetic field that induces either current or voltage in those detector. So that's how they can detect if you have a metal. There's many application you see, and then I can't wait to hear what you can come up for an application using this induction in the class.